Hi, all. Just giving you a little heads up on this reference sheet and thought I'd go through it and highlight the key points. You should grab a highlighter if you want to succeed and mark the points that I mark here. Draw. I think I got to get there. All right, here we go. And then, all right, we're good. Okay, remember how we started the year. Okay, so the graph is obviously increasing. As I read left to right, we're going up. Okay. So what does that mean about the rate of change is positive? Remember what we talked about. There's slopes of tangent lines. Slopes of tangent lines. I'm trying to draw these tangent lines as we go here. This slope is, let's just say it's like 1/2. And then this one's like 3. And then this one's like a slope of 6. Obviously, these are getting steeper as I read left to right. So that is, the concavity parts. But first of all these slopes are positive, so that is the yellow. But the second part is concave up. Look at those slopes as I move left to right. They're going up in value. All right, so that's what we mean when we say the rate of change is increasing. And then that also is synonymous with it at an increasing rate. So it was all that language we had before that I think we have done pretty well with. Wrong. You saw me with that thing. I hit that and it didn't activate. There we go. Complaining about the internet. Okay, and I'm only going to do slopes of tangent lines on this one and not the others. I do want you to understand that these are still positive slopes, but notice when I do these tangent lines, which skip right off the graph, those slopes are getting smaller. So this one might be 6. This one might be, I don't know, 3 seems a little too steep. Then this one's like only 1/2, meaning the slopes are much less sloped, I guess. Can't think of a better word than that. So trying to coincide with this, the graph is still increasing because the rate of change is positive. All those slopes are positive, but those are getting smaller as I move left to right. That's the definition of concave down. So that means the rates are decreasing, right? I think you remember that. Okay, so no more highlighting. Concave up, but these are going down as I read it. So the rates are decreasing, but concave up. Okay, I guess I will do this because sometimes this is conceptually difficult to figure out. That slope is steeper than this one. So let's say that's -6, -3. Let's make up slopes. But -3 is bigger than -6. So those rates are going up as I move. But you got it down. As long as you know it's concave up, that's what that means at an increasing rate. And it's certainly decreasing as I read left to right. Okay, so good thing there. All right, and then I'm not marking this one. This is concave down, and this is decreasing as I read left to right. All right, so those slopes are actually decreasing because they're getting steeper, so they're getting larger negatives. All right, done with that. Remember points of inflection, that changes concavity. So that's a simple concept. That's concave down. This is concave up. And then this is concave down. So those intervals. And you'll probably have to mark the x's. Where does that concavity change? That's where the x values are, which are not marked here, but you get the point. Yep, points of inflection. Good, nice. All right, and then the rates of change, average rate of change. We just did that today. So I'm actually taping this video after our last section where we did rates of change on polars. But non-polars, this is just the difference of y's over the difference of x's. That's just slope from Math 1. And you've done that so many times. Okay, going to move on to this little thing. And, feel free to ask in class if you want any other clarifications about what you read through here. But I felt like making this video to help you read through this and remember all the things that need to be remembered for each chapter. Chapter 1, 2, and 3. This is Unit 1. All right. Now, when I look at this, this is obviously increasing as I look at this. And then this is, in this example, concave down because these rates are going down as I move. All right, so just make sure you understand how to look at concavity in charts of values. A little bit tough. Not sure if that'll end up on the exam like that. You could honestly graph those points real quick. and then see the curve and see how its concavity is shaped. And that would actually work out as well. Very smart. Then you can compare it to these pictures up here. Which one do I have? 1, 2, 3, or 4? And in that one, you're going to have the third one. Third? No, second one. Because these values are positive, but as I move, these values are not increasing as fast, each one. That's what these first order differences show. So you'd have a curve that would look like that if you actually graph those. Smart way to do it. All right. And then a totally different thing with common differences. Remember, we did this with polynomials. 2 minus 1 is 1, so this goes up 1. This goes up 3. This goes up 5. This goes up 7. Then when you look at these have a common second order difference of 2. That means it's quadratic, or an x squared function would match this data. If third order differences were equal, then it would be cubic, and so on and so on and so forth. The second order differences also, if it was cubic, tell concavity too. So a second order difference that's positive would represent a concave up portion of the graph, and then vice versa for negative. So just remember that as well. Okay, complex zeros come in pairs, good to know. Multiplicity means we could have multiple zeros, or like I could have a zero that has multiplicity 2, 3, or 4, and I'll give you an example of this. I'll put it right here in the picture right above it. Questions that this dealt with were x minus 2 squared, x plus 1 cubed. What time we got here? Okay, good. We got 10 minutes in my third hour here. So my zeros are 0, because people missed that one. 2, but that's a double 0. And then negative 1, that's like multiplicity 3, 0. And then remember, this turns into x to the 6th, which is later. We're going to look at this down here next, polynomial end behavior. And x to the 6th, remember the polynomial dance, which you probably just did at prom? Those end up and up. All right. So how does that shake out on this? This is a multiplicity 3, 0, which goes through like a cubic. So it's got that little swirl through there. This is a regular 0, so it just goes straight through. My bad, dogs. I went the wrong way because this ends down and I did the opposite there. Did he do that on purpose? As far as you know. So it actually comes from up here and then goes through like a cubic, goes through, and then boing, 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 it bounces there because that's a multiplicity 2, 0. Multiplicity 2, 0, multiplicity 3, 0 goes like a cubic. This is review. So hopefully all this, you're like, yep, got it. So anyway, limit notation, we really worked a lot on that. I just haven't had it in a while. So remember these limit notations of what we have here, and I'll mark it here. As x goes to infinity, look at where y goes. So that is this one right here. That's what that mirrors. So I'll highlight that. I lost my draw. That's this end. Okay, and I don't know why some people had such a hard time with this. It kills me. All right, as you go to negative infinity, so as I plug in these values, this is where the y's go. That's why the y's go off to infinity there. So end behavior, kind of a, good thing. You can read through the other things. There's some multiplicity things. I went through that up there. Even odd functions. Remember, even functions are symmetric with the y-axis. Our most popular even function is the quadratic, y equals x squared. That's the symmetry sound. And then the most common odd function is, I'll switch the colors now, the cubic, because it looks like this, and it's symmetric with the origin. Okay, there you go. All right, so even and odd, and those are the attributes of an even odd function. Okay, I actually like this better. So when we did this, oh, the other teachers are probably going to be mad at me and turn me into the Gestapo. All right, but what we would do with this was actually make a sketch. So I'd get the zeros. One is at, I guess this doesn't coincide with this. -3. I think we got a problem here. Doink, doink. And then this graph should be at -3. So I think we have an issue here. And then this one is at 1. And then this one is at 4. -2 is just an A value, a stretch vertically. Remember that? Stretch vertically because A is 2. And then that negative is a flip. I should say x-axis reflection, but I'm shorthanding this. Because what we would do then is do a sketch of this graph. So here are our zeros. By the way, less than 0, I'd make them open circles. And then I would know that the graph is supposed to be x squared, cubed, 4th power, negative leading coefficient, polynomial dance would end down and down. So how this graph would look would be like this. And then it would go up, then it would go down. Look at the key right up there, right above here. We bounce here because this is an x squared, or an x minus 1 squared, a double 0. And then it would go up, and then down, and then this is a regular 0, and it would go through. Now, the simple way of input-outputting is less than are these values. Those are the values that the outputs would be negative, which are outputs that are less than 0. Again, this is review. You should be like, yes, I remember this. We got to make a change in these notes, though. Little bit of a mistake. So -2 is supposed to be -3, right? No big deal. And we did the same thing with rational functions, okay? All right, but I'm going to highlight this, and some reason we didn't memorize this very well, I think. Let's go to the easiest one. When the numerator's degree is smaller than the denominator, at this point, I'm not giving the y's. We got to remember that that's automatically y equals 0. Fine, I'll give you the y's. When I throw in a very large number in for x, like 100, 100 squared is overpowered by 100 to the 4th. So that makes the denominator very large. So what is very small over very, very, very large? 0. This is the y. The end behaviors as you throw in big positives and big negatives. The outputs approach 0, so therefore we put a horizontal line to show that behavior. All right, when these are equal, x cubed over x cubed, the hundreds would cancel each other and you would just approach -2/5. And we showed you that on graphs when we actually did this stuff. We would put the graph in y1 and put y equals -2/5 and y2 and show how the graph would come to that line on both ends, both far left and far right. So the limits of the end behaviors equals those asymptotes. Same thing over here. Okay, that's what we had to write. We had to write those limit statements. All right, and then the rough one, when the numerator's degree is larger than the denominator, you have a slant asymptote. And as far as you had to do, you just had to take these two and divide them. And then this cancels to be an x on top and no x on the bottom. So it's 1x over -2, which is -1/2 x. That's as much as you had to do as far as like denoting what is the slope of the slant asymptote. And then we did that. We put this in y1, we put this in y2, and you could see the ends of this graph would approach this linear situation. Now, that line kind of goes like this, negative slope like that. So the graph, whatever looks like in the middle, it could have come from this side like this. And then on this side, it could have come and went to this side. What I'm trying to get you to understand is these limits here. As x goes to -infinity, y went to +infinity. As x went to +infinity, this y value is going down forever. So kind of remembering that stuff. We're at 14 minutes. This will probably be the longest of all the videos. Zeros are numerators are equal to 0. Wholes are when you have cancel numerator and denominator. Vertical asymptote are zeros of the denominator. So things to remember here. This is a monster. This is like typical AP. So x plus 5. No x plus 5, so this stays. X plus 2 squared over x plus, or plus 3 squared. These both completely cancel. That means I have a hole there. All right, and I'm going to actually do a little bit more about these holes. X minus 1, x minus 1. This is left. 1x minus 1 on the bottom. And then this cancels, and this cancels. This is left on the top. So what do we have here? We definitely have a hole at 4 because of the cancellation. The only x-intercept we have is x equals -5, but it really should be said -5 comma 0 because it's a coordinate. And then the only vertical asymptote I have is the leftover at the bottom there, x equals 1. But what are these holes? I'm only going to do one of them. They're located at -3 comma, plugging in -3 into the leftovers. So -3 plus 5 is 2. -3 minus 4 is -7. -3 minus 1 is -4. Okay, that's -14 over -4. You don't really have to reduce, but I will. That's 7 halves. You do the same for 4. You'd plug it in and see what the output is in the leftovers. So try to remember that for holes. Okay, moving along. Factors in the denominator will never be a 0 of the function. True, that's a vertical asymptote. Okay, factors in the denominator always become a whole or a vertical asymptote. We just showed that. All right, the dreaded long division. Take a look at that. Remember, we take this times this and then subtract it. All right, so if I distribute that minus sign, this becomes 3x. Then I take this times this to match this and then subtract so I can get my remainder. And remember what we do with the remainder, which they didn't put here. We put a plus remainder over divisor as the last part. All right, so just real quick, long division. But if you had to find a slant asymptote, then you really don't need that remainder. I was just doing long division all the way through, so you understand that. But for slant asymptotes, we only care about this part. So y equals, it's already written over there, but I just wanted to clean this up a little bit. Me doing this the long way and showing you the remainder situation. All right, and then this last thing, we did not teach this year. We did see this on the AP exam this year. If you want to look this up on your own, go for it. You can just type binomial theorem in Google, and you'll get a nice little 5-minute description of that, okay? Just takes a long time to kind of like show that, and if you're worried about one and only one question that this may involve, go for it, okay? All right, hopefully this helps you read through that first one.